But we're going to start talking today about how energy is contained in substances and what it means to have energy, what it means to do work, all those types of things. So energy, if a substance has energy, it has what we consider the capacity to do work or produce heat. Okay, the capacity to do work. And we don't quite know the definition for work yet. I'm going to sidestep that for just a second, and I'll come back to that in just a minute. But we're going to study the law of conservation of energy, which if you were going to give the tagline of law of conservation of energy, it would say energy cannot be created or destroyed, just like the law of conservation of mass, right? For something to be conserved means that it can't disappear to somewhere and it can't come from nowhere, right? We've got to have it just changing form. So when we talk about the law of conservation of energy, we're looking at how energy converts from one form to another. The total energy content of the entire universe is constant. So we have a set amount of energy in the universe, and that energy is then just transferred all throughout everything, right? Have you guys studied like I don't want to call it the food web, but like I guess maybe it's called an energy flow, right? Sun makes energy for plants, and animals eat the plants, and we eat the animals, right? Have you heard that kind of stepping stone before? All of that is regenerative in terms of energy, right? When things break down in nature, right, it's restoring that energy back to the earth and all of that kind of stuff. But we see that energy just transfer from one to another. Can you throw out some types of energy that you've heard? What are some different categories of energy maybe you've heard of? Kinetic energy is one. Do we know what kinetic energy is? It's the energy of objects in motion. The prefix kina means motion. So kinetic energy is objects in motion. Good. What else? Yeah. Potential energy. Good. That would be considered stored energy. Any energy that an object has stored is considered potential energy. What else? Chemical energy, right? The energy contained within bonds, contained within atoms, things like that. Good. What else? What did you say? Nuclear. Good. Within the nucleus of the atom. What about electrical? Heat, right? Thermal energy, things like that. Light energy. We have all of those different types of things. And so we see energy just transfer from one type to another, right? When we eat something, our body converts that energy so that our body can function, and that energy will be then transferred out. Okay? All right, so when we have chemical energy contained within a reaction, we have something called endothermic and exothermic reactions. Okay? Endo means that we have heat flowing into a system. Heat is flowing into the system. Okay? That heat is not coming from nowhere. It means it's stealing heat from the surroundings. So you might actually feel the surroundings getting colder. Right? That whatever that system is taking heat from its surroundings, and it will then absorb that. An exothermic reaction means that energy is flowing out of the system, so the actual system itself, the thing, is getting colder, but heat is flowing out into that system. So that's considered exothermic. In order to satisfy the law of conservation of energy, it says that energy gained by the surroundings has to be equal to the energy lost by the system, right? That's just restating that law of conservation of energy, is that energy is not dissipating into nothingness, right? It's being transferred from one to the next. Okay? All right. Okay. Is freezing water an endothermic or exothermic process? Well, I already have it circled. Tell me why do we think freezing water is exothermic? Yeah, Maddie. Right. Heat is leaving the system, right? Letting that water, ice, whatever get colder, right? And so we see that happening as it leaves the system. Okay. I've got a couple other examples here on the next page that we're going to look at if things are endothermic, it didn't come, or exothermic. Okay. Classify each process as endothermic or exothermic. The system is underlined in each example. So we're really only studying the thing that's underlined. That's what we're focusing on. Okay, so if I put my hand on ice, is my hand endothermic or exothermic? Is it the transfer of heat? Endothermic or exothermic? What do we think? Because what's happening to the ice? When I touch the ice, the ice will melt. So the heat is leaving my hand and being transferred to the ice, right? Heat always flows from hot to cold. So when that happens, when I'm touching ice, that heat is leaving my hand and transferring to the ice. So now if we focus on the ice, is it endothermic or exothermic? Endo, right? The heat is flowing into that. Very good. Okay, water boils in a kettle while being heated on a stove. What do we think? Endo, right? Heat's moving into the system. It's pulling its heat from its surroundings. So tell me, it's specifically on a stove in a pan. Where is it pulling the heat from? The pan itself, probably, right? Because the pan is being heated from the coils, right? All of that's happening. The pan itself is getting hot, and so the water is pulling heat from that. That's why we use metal pans for cooking, right? Because they're really good conductors of heat and electricity. You don't use styrofoam to cook with, right? It wouldn't work. Okay, water vapor condenses on a cold pipe. So we have water vapor as like a gas or a vapor, and it's condensing. That means it's becoming a liquid. So what do we think? Exothermic, right? It's cooling down. Heat is leaving that water, and so it's cooling down. And then if I have ice cream that is melting, what do we think? Endo or exothermic? Endo, right? Heat's coming into that system and causing those processes to melt. Do we have a good idea of what we think endothermic and exothermic processes look like? Okay, good. All right. When we study energy and all of its transfer and conversions, that's called thermodynamics, right? So why do you think thermo is used for that? What's thermo mean? Yep, temperature, heat, right? And then just heat and energy kind of get used interchangeably, right? There's lots of versions of energy, but we tend to kind of use them. Interchangeably, okay? This equation given down here is the energy of a system is equal to the heat. Okay, so Q represents the variable Q represents heat, and then W represents what we call work. And we're going to go into that in just a little bit. I will tell you, we'll study this equation and this part of thermodynamics, but this is not really the main section of our chapter. So we'll get into it a little bit, and we'll understand kind of the overview of this part of it, but we really want to study the transfer of heat between objects a little bit more closely. So we'll do an introduction to this, but we're not going to spend too much time on it, okay? So Q represents heat, W represents work, okay? All right, thermodynamics quantities consist of two parts. The number gives the magnitude, and the sign indicates the direction of the flow. So that means if heat is flowing into the system, it would have one sign. And if it flows out of the system, it has another sign. Okay, so now when we say it has negative 78 joules of energy, right, we can't have so little energy that we have negative 78, right? We can't have less than 0 energy. So the negative here is not a numerical value. It's a directional value, right, going into or out of. Does that kind of make sense? The negative here is not indicating the numerical value less than 0, because we can't have less than 0 energy. Would we agree with that? Right, you have 0 or you don't. Okay. Heat is given with the variable Q. Sorry, just on that last slide. This unit right here, capital J, is called joules. And that is the unit for energy. Okay, that's the unit that we give at the end of our answer. It's just a capital J. Okay, and joules comes from a combination of other units, but we're not going to get into that, right this second. Okay, let's look at how the direction works here. If you have a positive heat value, heat means it's going into the system, so that would be endothermic, which I'm glad because that makes sense, right? Positive heat flowing into the system. And if heat is leaving the system, or we have a negative Q, that would mean that it is exothermic. Okay? So that negative value just shows us the sign in which it's going, right? Which direction we are moving here. Okay, I'm going to just kind of breeze through these next few slides about work. Work is kind of a tricky concept, and although it's important for us to understand at higher levels, where we're at right now, it's not a major component of what we need to study. So I want to give us a little bit of a background with it, but if it's not making a lot of sense, we'll be okay, okay? So the work done by a system or on a system is how we calculate work by looking at the pressure change versus the volume change. Right? If we have a particular system and we have a pressure change and a volume change, we consider work to be done. Okay? When we learn about work in physics, is some object displaced because of something else, right? Did I cause, let me give you an example. If I push this object, I've done work on that object. I've made it move, right? I applied a force and made it move. I can push on this wall all day long, but I'm not doing work because it's not moving, right? So there's a difference from what we consider like, oh, I'm working really hard, and the actual scientific definition of work, right? So I'm not displacing the object, which means I'm doing no work. Same thing is true here, right? I can push this down, but if it's not moving, I'm not technically doing work. So when we see the term work, it means that an object has been displaced. It's been moved in some way, okay? And that's kind of a broad definition for it, but that's what we're looking at here, okay? So if we see volume expanding, we consider it negative work. And if we see volume compressing, we consider it positive work, okay? Because, let me dive into this and why this is true. Do you know what this delta, this little triangle here means? Let's take a deeper dive on that. Do you know what that little triangle represents? It's a Greek letter delta, and it's going to become really important for us. So go ahead and write that down. This Greek letter delta is one we're going to use a lot. Okay? And it means change in. Okay? So when it says delta V, work equals pressure times delta V, it means pressure times the change in volume. Change in volume. Okay, so we're not just looking at the volume at a particular time, we're looking at the difference in volumes. Okay, so let me be a little bit even more specific here with change in. It really means final something, whatever it is, minus initial. Okay, the final volume minus the initial volume. Okay, do you see what we're doing there? We use delta a lot in science. In physics, we use it a lot. So I can solve for delta V, that'd be the change in velocity. Delta T would be the change in time. So this delta character right here, we use it a lot. And it always is going to represent change in, okay? Or more specifically, final minus initial. So highlight that, circle it, whatever you need to do to kind of remember that delta value. That's what that looks like, okay? So now let's figure out when I'm expanding volume, I have negative work, and I have, if I'm compressing volume, why would my work be positive? I said something incorrectly. Okay. When we do this, our value is going to come out in a different sign, because if I'm expanding my volume, let's say that my final volume is 30 and my initial volume is 10. When I go to solve for work, I would have some pressure. Let's just say my pressure was 2 atmospheres. I would take 2 times 30 minus 10, right? That value is still going to come out positive. So we add a negative on there, okay? And that's a little bit counterintuitive and something that we don't need to necessarily dive too far into, but my work here for an expansion would be negative 40, and it's also measured in joules, okay? So you can highlight this little section right here where it gives you a little clue. When we write out an equation sheet for this chapter, I'll kind of give you a little sheet to write down equations. We can have that on there as well to kind of remind us. When the volume goes up, we would have negative work, and when the volume goes down, we would have positive work. So we would kind of just stick a negative on the front there, okay? why don't you go ahead and calculate the work associated with the expansion of a gas from 46 to 64 liters at a constant pressure of 15 atmospheres. Have we seen this before? Atmospheres, when we studied what? Do you remember? Stoichiometry and gas laws, right? When we did gas stoichiometry too, you did that this semester while I was gone, right? So ATM stands for atmospheres, and that's our pressure unit, okay? So calculate the work. So we know work is equal to pressure times delta V. And this particular one said it's expanding. So what direction do we assume that our work is going to be, positive or negative? Negative. So you can even tack a negative on the front there if that's more comfortable for you. Okay, so our work value would be equal to the pressure, 15 atmospheres, and we know it's going to end up being negative at the beginning, times delta V. So am I going to take 46 minus 64? Or 64 minus 46? Do you remember? How am I doing my subtraction there? 64. Okay, so it's so easy for you guys to see these numbers and just go, oh, here you go. Here's my volume difference, just because that's how they're listed. But we have to make sure we're really, really careful of thinking, this is my initial volume, and this is my final volume. Okay, so I'm going to go 64 minus 46, and I'll run my math, and let's see what we get. 64 minus 46 times 15. So we get a work value of negative 270, I think. Is that what you had? Okay, and that is also measured in joules. Okay, so energy, work, and heat, all of those things associated are measured in joules. Okay.
So what does delta do?
Delta just shows that the math we want to do is the final minus initial. And so this is all just multiplied together. It's P times delta V. Okay, so delta V is right here. Change in volume, right? Final minus initial. But it is all multiplied together. Okay, so that's just not shown. You could put parentheses around there if you want. Okay. Did you put this equation on your equation sheet as well? You might want to put that one on there. Okay, work equals P delta V. All right. Let's look now at a new term and a new concept called enthalpy. Enthalpy, okay? Enthalpy is a quantity equivalent to the total heat content of a system. So any sort of heat we have in a system, it's equal to the internal energy of the system plus the product of pressure and volume. So it's the heat plus the work, right? It's all of that stuff. So enthalpy is given with this delta H, okay? And actually, I'm going to take that one step back. Enthalpy is represented with a capital H. Okay? I know it's counterintuitive, but we can't use E because that means energy, right? And enthalpy and energy are a little tiny bit different, okay? So enthalpy is the total heat of the system, internal energy plus the product of pressure and volume. So enthalpy, right here, capital H, is equal to the heat of the system, which we just looked at, Q. Right, we looked at that a little bit ago. What does this delta mean then? The change in, right? Change in heat is equal, change in enthalpy is equal to Q. If I want to look at a chemical reaction and how the heat changes, I might use this system right here. The change in enthalpy is equal to the enthalpy of the products minus the enthalpy of the reactants. In all the work that we're going to do coming up, this value really has already been calculated for us, right? They've done these calculations, and now they're just like data tables full of enthalpy values, right? Of how much energy is transferred or changed in a chemical reaction. That data has really already been collected. So this is kind of just showing us what that delta H means, right? It's the change in enthalpy of our products minus our reactants. So most of that calculations have been done for us already. And then we're going to use this value and to be able to calculate, okay? Positive, we said, is heat flowing in, and negative is heat flowing out. So that's the same thing that we saw with Q, right? Because H and Q behave very similarly. Let's try one here where we actually are going to calculate delta H. Okay, we're going to try one where we actually are going to calculate delta H on our next slide. Okay, so let's look at this next example. Consider the combustion of propane. So here is a balanced chemical reaction where we're taking propane gas and burning it with oxygen to form carbon dioxide and water. So it's a combustion reaction. And it says that our delta H for the entire reaction is negative 2,221 kilojoules for 1 mole of propane. So this value has been calculated already. Okay, this value right here is how much the heat changes when this reaction goes on. Okay, for 1 mole of propane, which is that what this reaction calls for? Does this balanced reaction just call for 1 mole of propane? Yes, right? That's the coefficient that sits there. So this is the reaction, the delta H for that particular reaction. So this says, assume that all of the heat comes from the combustion of propane. Calculate delta H where only 5 grams of propane is burned. So if we know that this much heat is transferred when 1 mole of propane is burned, we need to figure out how can we find out how much heat is burned, how much heat is transferred when only 5 grams of it is burned. Okay, so let's look at how we can examine this. Let's start with what we know. 5 grams of propane, which is C3H8. And let's convert, right? If this is our amount of energy transfer for 1 mole, I need to get 5 grams to moles. Right? So I've got to get rid of grams and go to moles. Okay. Are we on the same page so far? Right? If I know that 2,000 roughly kilojoules of energy flows out for every mole of propane that is burned, I've got to get my grams into moles so I can start comparing. So let's see, grams, I don't know, molar mass here is probably 44. Okay, and so I can find out how many moles, but I'm actually going to keep my chart going here. I'm going to keep pushing this stoichiometry a little bit more. And I'm going to say that for every mole of C3H8 that is burned, negative 2,221 kilojoules of energy is transferred. Right? I'm just kind of extending that chart a little bit, right? I could stop at moles and then do my math, but I'm just going to kind of try to keep it going, right? This is the conversion factor basically that was given me in my problem, right? I'm told that for every 1 mole of propane, I'm releasing 2,221 kilojoules of energy. So now I can just do my math, right? Because I've canceled grams, canceled moles, and I'm left in kilojoules. All right, so 5 grams times my energy divided by 44. I get about 252.4 kJ. Does that kJ make sense? You know what I mean with that? It's just kilojoules, just like you have kilometers or kilograms, right? It just means that there's 1,000 joules found within that.
Always end up in kilojoules?
Mm-hmm. Yep. As long as our starting amount is in kilojoules, which a majority of the time it is. Yep. Does this number seem to fit our expectations? At least, did we expect it to be lower than 2,221? Yes, because that would assume a whole mole is done. We know a mole of it weighs 44 grams. And so 5 moles of that is like, 1/8, somewhere around there. So we're, saying, can you kind of walk through what our expected values were going to be? Okay, does that at least make sense that our number was lower? I hope. So So that's how much energy is released if we only burn 5 grams of that propane substance rather than a whole mole of it. Okay, any questions with that? All right. All right, when 1 mole of CH4 is burned at constant pressure, 890 kilojoules is released. Calculate delta H for a process in which 5.8 grams of methane is burned. Okay, so this problem is very similar to the one we just did. I'm going to give you about a 2-minute head start, and we'll see if we can match up here in just a minute. Let's see, is that similar to what you had? Does continuing that through the chart kind of make sense to everybody? Right? It's almost like I'm just doing a proportion, right? If 1 mole produces this much, then how much does a smaller amount produce, right? That's really what we're looking at there. Okay? Tell me what questions we have with that. Okay.